and packet forwarding application specific integrated circuits, critical components powering high power performance network systems. In addition to his technical contribution, he has successfully filed 10 patents reflecting his innovation and expertise in the field.
That's great. That's great, Harshad. G- very nice achievement and technically advancement is there. So we are really proud of you and really thanks for having this, accepting this session for as a resource person. So I request you to start the session.
Sure. So first of all, thanks, Manisha madam. I think when we spoke last week, I was in Mumbai when there was my attend some marriage, and I was thinking what kind of content I should create uh, for faculty and students both. So I hope the content which I've created helps you uh, gain some knowledge and gives you a lot of pointers to search on net that what people are doing. And that's why when Manisha madam asked me for a topic, I thought I'll keep it very specific to networking. Okay. Uh, and that's the content I've created. Again, thanks Ameya and Manas. I would not have been able to say so many things about myself. So thanks. So both Ameya and Manas are students or
Yes,
okay,
yes,
okay, okay,
yes.
okay. And I could see around 30 people joined. So most of them are students or most of them are faculty or it's like,
Faculties
okay,
are
okay,
there.
okay, okay, great. Okay, so let me share my screen.
Yes.
So this is my wife's laptop. Okay, so that's why you see her name uh, uh, wherever my video is. Okay, so another thing which I would like all of you to do is if you don't understand something, you can raise your hand or ask question. I will also more interactive the session is. It is more good for everyone. Uh, I think there is a time limit of 1.5 hours, so we'll try to keep it till 5:30. But ask questions. A lot of things because we don't work in the same field, so you may not be knowing terms. I would try to explain those. Okay. Okay. So I think the about me part is already done. The only thing which I'll add is like when I shifted from Tata Honeywell to electronic design, where because I wanted to do the word VLSI in 1999 was not famous. Okay, at least in India, and somehow in 1996 or 1997, CDAC had identified that in India there is people don't know what is VLSI. Okay, we'll come to that in one of the slides what it means. Uh, and the reason why CDAC understood that because and it's very relative in today's times. In 1991, we were sanctioned around 91 or 92 by the US of not able to buy uh, uh, any kind of computer, supercomputing material, supercomputer processors. We were completely banned, and that's where CDAC was formed to actually develop a supercomputer in-house, rather developed by Government of India. And in that period of 10 years, that decade of CDAC, where you would see uh, that we actually developed, CDAC actually developed chips, processors, and networking elements, build a supercomputer. So I don't know whether you can visit CDAC Pune, but there are those systems available which were built in the last decade of last century. Okay, people actually built those. Uh, Most of those people actually went on to build great careers outside India in Cisco and a lot of places. They came back also, some of them. So, so they understood there's a need that people don't know how to do designs, very specifically digital designs, and that's why they started this diploma. So I could be like a third or fourth batch. One of my friend from VIT, my batchmate had done this course, and he told me good thing about that. That's how I want. So that's how things change. We don't plan the, oh, I want to do this. I only knew that I want to do something in electronic design, and I entered CEDAC. So that's the only additional thing that information is missing. Uh, the reason to say this is if you're a student or if you're a faculty member, you may want to change your career. Do There's always ways you can do it. It's not impossible. This course was designed such a way that I left job, but one of my friend actually did not leave his job. So he was a software engineer who wanted to come into electronics. So he used to work from 9 to 6. Our class used to start at 6 to 7:30, and from 8 p.m. we used to have labs. So labs were the FPGAs, and you can do your design implement. And we used to do lab work from 8 p.m. Take a dinner break till 1 p.m. 1 a.m. 2 a.m. And then used to sleep there. We used to go back home. He used to sleep and go back to office the next day. So there are a lot of inspiring stories. And this guy is a very successful engineer at Texas Instrument now. But he worked 3 4 years in the software industry, then shifted to this way. Okay, patents is something I may not be able to talk about it today, but it is something which I think a lot of faculty members would definitely would aspire to do, right? Uh, uh, it happened to me also in last 10 15 years that I filed 10 patents. Earlier, we attempted one or two, and there various reasons we couldn't do it. Uh, but but the whole process of doing patents is a very interesting process. Basically, finding a solution for a problem and then saying that this is a unique solution which no one is doing, and it could be very simple thing which we feel that what's there in this idea, right? Uh, I'm saying this because I'm part of a committee in my organization where we decide whether the idea is worth patenting or not. And I would think VIT may be having such committees where they may be doing some original research and maybe trying to apply for a patent. So you can participate in those activities. You may get rejected. I have a lot of my ideas got rejected. It's not like that, but going through that process is very good experience. Okay, so let's now come to our real topic of today, which is ASIC and the application use case, right? So before we jump into the topic, let's try to see a chip, which we now use very commonly, the word chip, or a integrated circuit industry, and how it is split into. You would have seen so many different companies are there. So let's try to first put them into different baskets, and we'll take it from there. Okay. So the first type of companies which are part of this industry is the foundry, okay, where actual semiconductor manufacturing happens, and a lot of you would have heard about a name called TSMC. So, so this company, which TSMC only manufactures a chip. They don't own any chip. So you would not have heard a TSMC processor, right? But every NVIDIA chip is manufactured with TSMC. So they are only doing the manufacturing. They don't own any chip. Now, another type of industry, which is another type of player, I would say in the industry, is a fully integrated semiconductor company. And these are the companies which make design the chip and also manufacture them. So Intel, everyone knows, and Texas Instrument, and there are a lot more. It's not these two, but these two have a very successful fully integrated play where they design their own chips and they actually manufacture and then they maintain the entire thing. The third category is what we're going to talk today about is the fabless semiconductor company. Okay. Uh, Now this is a very interesting category. What category this is that these people sell the semiconductor. So they will sell the chip like a NVIDIA GPU, Broadcom switching chip, Qualcomm SoC for mobile. They sell the chip, but they don't own any fab, and that's why they are called fabless. But they're purely semiconductor company. I should not have taken name of Nvidia here because in last few years, Nvidia has actually become a system company also. They're also actively building systems company. And the last category is the last category is a systems company developing chips. Okay, hey Manisha, madam, you're getting my slides, right? Because I just closed the other window. Hello.
Yes, sir.
Yeah, yeah. So I'll not be able to see if anyone raised hand. So I'll just wait here. So if anyone has a question, I'll answer it here and then we will go to next slide. Is there any question? Then the systems company case, what happens is, like Apple, Cisco, Juniper, they are not selling chips. So that's why we are not calling them semiconductor company. If the company which I work for is Juniper Networks, we sell the entire system. Like Juniper sells routers, switches. Apple sells a mobile phone. But what they see is they need to develop a chip which they need for their own product, which is a differentiation for them. Even in last 10 years now, Amazon, Google, they are also developing their own chips. Okay. uh, and that's why I've put them into different category. You if you go to them, they're not going to sell their chip to you. They're going to, they are developing for their own product, and they sell the product, the end product. I hope there's no question. Should I check on the chat window? There's no question, right? Okay, fine. Okay, so then let's move on. So we are calling this ASIC is actually a application specific integrated circuit. Okay. Uh, then the first question will come to our mind: why ASIC? Why someone will go ahead and develop this kind of a chip? So in a real world use case, right? There could be, let's say, as a Apple, they build a smartphone, and if you remember when they initially launched their iPhone, it used to be based on Qualcomm. Okay. Qualcomm chipset. Now, as they went on their journey of this developing a next better solution, uh, they figured out that if they could develop their own ARM core, and if they could develop their own SoC for their own iPhone, they could really show a differentiation to the customer, and have lot better performance. So that is the driving criteria for some company to go and uh, decide to do their own ASIC. In case of Juniper or Cisco, what happens is the type of products which we build. So why I'm talking about this? Because what I told is a third category of companies which are selling semiconductors. So a systems company who is actually building a product can buy a chip from that vendor and build a solution. That is possible, right? But sometimes what happens is that solution is not available. Whatever I want to build, it's not available in the market at all. So then I don't have any other choice than to go ahead and actually develop this chip and then build my product. Similar thing happened with Google in some 10, 12 years back, when they started doing machine learning first, and they figured out that using x86 process is not going to solve this problem. Okay. And GPU could be overkill. It will take a lot of power. And so they developed their own TPU chip. Now, a lot of people talk about their chip TPU, but they're doing this, if I'm not wrong, from 2012 or 2015 timeframe. So they went ahead, developed that, they deployed. No one came to know because it's running, the search query is running lot behind GPUs, the Google servers. We even don't come to know what's going on when we search on a Google browser or a Google engine. Similar Juniper, the scale of routing which we do, it's it's impossible to find a commercial solution, commercial available chip for doing that. So we have to go ahead and do it. We cannot do it using x86 anyways. Okay. Next important question is, okay, we decided that we want to do ASIC. We want to a company decide that we want to do ASIC. Then how is going to develop? Because that is not its the company's core competency is not semiconductor as such. So what all things it needs to do? It needs to first study the market, and parallelly then define the architecture of that chip, how the chip is going to be. Uh, this will involve a lot of things like what is the end use case, what's the system design requirements, and what is the software architectures of the system. So anyone who is designing any chip is always going to have a software control on top of it. Okay. Or the software could be running on the chip. So a lot of things get driven by that. So having use case, when I say use case, there could be use case, but there should be a justification for the volumes. Probably we'll come to that part a little bit later, the cost of doing this thing. And what kind of system in which this is going to go. So how I'm going to cool, how much power delivery I need to do, and what all features I will support. So all this that company needs to do before uh, before it actually goes ahead and finalizes how this chip is going to happen. Now, typically, if this use case is very generic, okay, there will be definitely someone in the semiconductor industry will always be doing this chip, because if the use case is very generic, like Qualcomm makes a lot of SoCs for mobile phone, right? Someone can argue, oh, Apple can still use that, and that's what happens with a lot of Chinese mobile player or Indian mobile player. They just use the Qualcomm chip or MediaTek chip and build their mobile phone, right? But so so if the chip is generically available, then you probably not develop ASIC. You will not develop a in-house chip. But if it is not generically available, then you'll do it. And those normally cases don't have millions of volumes. Normally they have thousands of volumes. Okay, uh, and a chip normally takes, and I'm talking about complex chip and not smaller chips. They take like 3 to 5 years of period before for the time you start planning and designing. Uh, Coming to lab, actually making a product normally takes 3 to 5 years, depending on the actual complexity. Now, once you decided the architecture, once you decided the decide this is how I want to go, you start doing design and verification of this whatever architecture you had in your mind. You're actually going to go to do the design and verification of that. Now comes the basic question that, okay, you are a systems company, you don't have your own fab, right? Uh, then how are you going to convert this design to gates? Okay, how a multi-million gate digital design you're going to develop? So what has happened in the industry is, for ASIC players and so most of the semiconductor players also, the design methodology used is called standard set library based design. Okay, so let's see what is the standard cell library is. So what happens is, as we said, there's a fab which is manufacturing the chip. Okay, and there's a systems company we want to develop the chip, and there has to be uh, some standardization between them, right? So what happens is, there could be a third player, okay, which called a ASIC service provider player, or the fab itself design something called a standard cell library. Okay, it is just a collection of pre-designed, pre-verified, and pre-characterized logic gates. So it will have AND gate, OR gate, flip-flops, buffers, maybe little complex AND gates. But these are pre-designed, pre-verified, pre-characterized. So what the standard cell library designer will do? He will actually design the transistor. Okay. So if you would have studied how AND gate is designed using a FET, right? Whatever transistor technology that would 3 nanometer, 5 nanometer ability, will you use those uh, transistors and develop the AND gate, develop a OR gate or a flip flop. Then he will characterize that gate that, hey, in different corners of the process, what is the delay through this gate? What is the strength of AND gate? So in this standard library, he may have different AND gates that, oh, if this AND gate can drive one another gate or two another gate or four another gate. Based on that, they will have a X2, X4, X8 variant of that AND gate in the library. The other thing they will do is, if you think of a chip or a wafer, it is actually drawn in a 2D way on the planar. It is drawn, if you draw fixed rows on it, okay, the row height is fixed. Okay, so when you place these gates on this wafer, think of it imaginary that we have drawn a lot of rows on a wafer. So the height of the row is fixed. So what these standard cells will do is, their height would be fixed, but their width could be varying, because if you want a more drive strength, you need bigger transistor. So your width would be bigger. So most of the gates, the height would be fixed. Now all this is done because uh, when you actually do the layout, okay, uh, there are standardized tools from vendors like Synopsys and Cadence, which are going to do the placement and routing of these gates. Okay, so we said that we generated the design mostly in Verilog or System Verilog, and someone else's EDA company's tool is going to convert this Verilog into gates. And then those gates I'm going to place, I'm going to automatically route them, because what a circuit is, right? You will have a lot of and or AOI multiplexers, adders, subtractors connected to each other and connected to some flops, right? So when we place them, now we have to find ways to connect them with each other. So the tools will automatically do it. So another thing, maybe you already know, but I will still explain the conceptually. In a chip, basically we have the base layer where there are gates are placed, and on top of gates there are multiple metal layers. So 8, 12, 16, and those metal layers allows us to connect this gate to each other. So the standardized routing algorithms knows this structure, that there's a base layer and there are metals on top, and on further on top of it, which layer, which metal layer has horizontal wires, which metal layer has vertical wires, that is also fixed. The width of the metal, the distance between the metal is fixed. The rules, in the if you go deeper into the place and route, there's something called as DRC, which drives this machine, drive this algorithm. There are rules that how this metal layers or metal routes are need to be laid. It's very similar if you have looked at a PCB routing. If you think nowadays PCB has multiple layers, right? So if your component is on the top, multiple components are there on the top. If you want to connect, we go on the other side of the PCB if you have a single layer. But if you put multiple layers, then to the via we will put a hole, uh, fill it with metal, and then we'll go to another layer. From that layer, we'll go to another layer. So we get routed. The ASIC structure is very similar. There's a base layer, there are metal layers on top of it. So most of the standard libraries will have all the standard basic gates and some complex gates like AOI, OAI, multiplexer. The synthesis tools, when they convert the Verilog or system Verilog into gates, they will their algorithms will try to optimize the gate use, okay, based on various criteria to put minimal number of levels, okay, between two flops to achieve timing and all that. And definitely there will be flip flops, there will be latches, there will be special clock cells, okay, uh, in any chip which is a synchronous circuit, okay, and a lot of you would have already studied and known that the flip flop would need a clock, right? But the chips which we are talking about today, we may have 100,000, uh, sorry, few million flip flops. Okay, so all these flip flops on that chip needs to be, the clock needs to go and reach to every flip flop, right? And in a digital design, uh, when you analyze path between a flip flop and another flip flop, uh, what is the arrival time of the clock at both the flip flops is very important, because if there is a skew, your your capability to run it at a particular speed may degrade. Okay, if the so what it means is this whole clock network or delivery of the clock to every flip flop in the design becomes a very interesting problem to solve. So different chips, different projects, and different companies have different methodologies to clock. A common word you may hear is called CTS. Okay, uh, so how the so sometimes the tool also have auto clock routing algorithms and they can use, but sometimes some companies use their custom method to route the clock on the chip. So they will decide how they want to do it. And these chips also use a lot of SRAM. Okay, so what's a SRAM? So SRAM is a denser memory element. Okay, which is very fast. Okay, it's not the most dense available like a DRAM, but it's dense. It's instead of grouping some, let's say I want a storage of uh, 2000 or 4000, uh, around 4000 bits worth of storage I want. So I can do it using flip flops, right? I can put flip flops into rows, let's say 64 wide and some 32 deep. So what these vendors do, or what we do is, we the library element designer will design a SRAM which is lot more compact than actually design a flip flop based storage. And And most of these designs have tons of SRAMs, uh, which gets used. Okay, and there are different categories into SRAM, whether you can access every cycle, whether you have read ports, write port, or whether there are how many ports you have and all that. Okay, maybe I'll stop at this point, and if you have any question, you can go ahead and ask. Okay, I don't think there's any question, right? Should I go ahead, Manisha madam?
Yes, yes, yes.
Okay.
Basically, ASIC means if a company wants to develop their own product
Mm-hmm. Yes.
according to their need and
Hmm.
custom built. That is the two main thing related to the ASIC.
Yes, yes. It's
Okay,
application specific integrated circuit. Yes, that's
okay,
right. That's right.
okay. Go ahead. Go ahead.
So these are the various step nowadays in a multi-million gate design happens. We do the architecture development, and then sorry. Then we do the design verification using system verilog. Uh, and there's a loop here. So we'll do synthesis placement to meet timing of the design. And parallelly, if there is a issue, we will change our design. Parallelly in the verification, we are trying to find bugs and refine our design to uh, improve the design. And so these two things are happening in parallel. So you're doing design synthesis placement, you're doing design, you're doing verification. There's a new concept which have come nowadays called emulation. So what happens is when you design a multi-million gate chip, okay, the verification time or running a test using such a complex digital design take a lot of time. Just to simulate 20, 50, 100 microsecond worth of a design may take 2 hours or 3 hours. Okay, that's and on a very pretty good Linux machine which is having very good RAM, very good Xeon processor. It still takes that much time. So what is happening now is like the bigger the design, the slower the verification. So the verification now we measure in terms of like how many nanosecond per wall clock we are running. So the simulation time may run 8 hours, 10 hours, 12 hours. And in that whole time, we may not be even able to simulate few millisecond worth of traffic. So emulation is an intermediate solution where people actually convert the design into some kind of FPGA. Okay. And that design actually works at 50 or 30, 20 to 50 or even few tens of megahertz. Okay, which speeds up the simulation by like 20x. So whatever you were not able to do 12 hours, now you can do it in 20 minutes, 30 minutes. And that gives us a lot of confidence. The most important thing in the chip world, who is going to entering in this field, is to know is that once you design something and you tape out and produce it, okay, you cannot change whatever you design. Okay, uh, it's a very dangerous thing because in software what happens is we can write any code, we can change it, we can recompile it, and even we can send if the software is what we're delivering to the customer, we can always recompile and give it. But in case of chip, it is not possible. Once it is done, it is done. Okay, the only option is you have to respin the chip. Okay, and and the cost structure of a chip is such that once you decide you want to do a chip, you have to pay what we call a non-recurring engineering cost, or the word famous in the industry is NRE. So we would have upfront paid a NRE to a fabrication. And if you are, we talk about 3 nanometer, 5 nanometer, right? For such chips, the NRE nowadays goes in the range of tens of 20s or $30 million. Okay, so once you do that and once you produce a chip, if you think that, oh, there is a problem, I have to respin, you may have to pay again the $10 million because the whole process of manufacturing involves a lot of mass creation and stuff like that. You can go and search on net to figure out how a taped out chip is manufactured by TSMC or any other fab. There is a very standardized process in this. All those masks in a very simplistic word in the long time back, we used to take photos on a using a camera, and then we used to develop the role, right? There used to film and that used to be developed. Similar stuff happens in the chip industry. There are mask gets converted, mask get generated for each metal layer, those metal layer, using those masks are cut and all that. A lot of stuff goes on. So the cost of producing chip is very high. On top of it, if you respin, your entire budget will collapse. What it means is, whatever design you've done, you're saying I have full confidence that there is no bug. Okay, I have all possible scenarios I have verified for that design. So the verification becomes very, very, very crucial in such projects. Okay, so never say that chip verification as compare it with software testing. Okay, it is, it's not like that. It's a lot more sophisticated job, with lot more efforts and lot more commitment needed to say that the design which I am verifying definitely doesn't have any bugs. So this whole loop which happens in any chip is a very crucial loop. It goes on for 6 months to 1 year if you're doing a brand new design. Okay, to make sure that we are not leaving any bugs. Everything which is specified, it's working as per that. So you can create test scenarios, different tests. So to just give an example, when Juniper does a chip, we run what we call regression, where thousands of tests are running for every module. So let's say in my chip there are like 10 modules. For every module, there could be at least 500, 600 tests running over 3 months, 6 months period to analyze different scenarios. Is there any question? Okay. Now I'll change the topic a little bit. Let's now go to the networking ASIC industry part. Okay, and try to see uh, what all types of chips, or what all type of chips are getting designed and used. Okay. So the first type of chips which are getting designed, and which most of you may be aware of or already using, is the moderate range high-speed Wi-Fi router chip. Most of us at our home may be having a broadband network, right? We see a box at our home which allows us to connect to the internet, right? And this gives us, okay, I'm giving an example of 200 Mbps to 1 Gbps, but if you do speed test, you'll see you get 50 Mbps depending on what is the wire on the other side. So again, inside this box, there is very custom specific chip, and this is designed mostly by the semiconductor companies because these are sold in volumes, right? Because every house needs a Wi-Fi router, so billions of devices gets produced, which allows the income, which allowed the cost to come down, because we even get routers at 2000 rupees. The chip is still there inside, but because volumes are very high, the cost comes down. Now, other thing which some of you may be aware of, but not definitely seen, is the wired network, right? Because the wireless network has become very easy. Even in probably VIT, we would have this called as endpoints, access point APs. May have been stuck at a lot of places on top of your head where there's a wireless access point are there. They're slightly different. The wireless access point are slightly different than the Wi-Fi chips or Wi-Fi products which we use at home. But wired network is actually predominantly Ethernet switches, okay? And wide variety of switch ASICs are available. Uh, the variety is in terms of a single device supporting 500 gigabits capacity to all the way up to 50 terabits capacity are available. So these are very big numbers, okay? We are talking about 500 gigabits to 500 terabits per second, okay? And where they're used. So they get used in campus networks, data centers, and GPU networks. Campus networks, like if I remember, VIT used to have 3 different buildings, right? And and all those building gets connected through a network. So that we normally term as campus network. There could be a lot bigger campuses, uh, or if some there's an office somewhere, right? And they may have multiple buildings, multiple floor. So they all get connected. You may see that there's a access wireless access point on the top, but behind that wireless access point there's a wired network which allows all these people connected together. Okay, the next type of devices, probably a lot of you may not know, is the routers. Okay, very few players, but these are sitting way deep inside the carrier networks. So carrier networks, in India, you know about Airtel, you know about Jio, right? But what are these carrier networks, right? We all said that we connected through the broadband network, right? or we go out, we use 5G and 4G, right? There are antennas all over, we connect. But there is a network behind it. Okay, so if you know about cell network, how cells are formed, there's a hexagon at the center of it. There's a there's a transmitter setting, and in that cell, when you go from one cell to another cell, your call get transferred to the another cell and all that. Behind all this, these towers which are there, they're connected through a fiber optic network. Okay, and when this fiber optic network connect, they terminate at a router. Okay, so what happens? We are sitting in Pune. I am sitting in Bangalore. Right? Let's take this example, and I am able to talk with you guys. Right? So we are talking about right now how this data, okay, the audio signal, the video signal, which is getting converted into packets, okay, which are reaching every one of your device. Right? So at the same time, when I'm speaking in real time, all this data is reaching to every one of your device. You could be seeing on a laptop, you could be seeing on a mobile phone. There are routers sitting. I am sitting in Bangalore. Most of you are sitting in Pune. Someone could be sitting somewhere else. So all these cities are connected together through routers. And in today's world, all these are VIPs. All these are using IP networks. So all these are s- packet switch networks. So these routers, okay, are doing this job for us. They are where they we don't see them, but they're sitting into the carrier networks and they're doing this job. The capacity of the routers, okay, increases manifold because the endpoint connectivity speed is increasing. So long time back, who of my age would know, we started with 2G, right? Barely used to connect on internet. From that, we are at 5G, where the we getting megabits per rate on the mobile phone, and there are thousands of mobile phones connected. If you guys have observed, when you see a match, a cricket match, if you watch cricket, the when you see a match on a application, they show a number on top, 1 crore, 2 crore people watching simultaneously, right? So all that telecast, okay, in the past, when you used to see it through DTH, right? It was via the satellite transmitted, caught by our dish which is close to us, and we used to render it on the TV. But now with the VoIP network, with the Geo application, right, the packets are sent over the internet and we are able to watch it. Okay, so if you think behind it, the capacity of these routers where is massive. Okay, so one of the chips which we developed is actually having 28 terabits capacity. So a single package having 28 terabits capacity of routing. Today in industry, 100 terabits per second devices are getting designed. Okay, so we are going at that rate because the capacity always keeps increasing. Now in the wired network space, what happens is there are very few people. I think this kind point got repeated, and this is where the ASIC comes into play because Cisco, Juniper, Broadcom, they have to design very specific chips. These are not chips which are going to be sold in millions of volumes. They are sold in thousands of volumes. So they have to design their own solution, first to solve the problem and second to show the differentiation that yes, I am able to do. And there's always a fight that who has the fastest device first and all that. The last thing is very interesting, and it has happened in last 10 years that there is something called as HPC. I told you I worked in CDAC a long time back. So this HPC stands for high performance computing, and there is nowadays called GPU networks. Okay, everyone is aware of AI. Everyone knows OpenAI. Everyone talks about Claude and all that. But behind this, okay, on what it is running is a true GPU based distributed compute system. Okay, it's not a single GPU on this which is running. There's a bunch of GPUs connected via network. And these networks and the network interface cards uh, are, are different than what used to happen or what are used in the data center networks. Okay, these are very high capacity, low latency networks, and they were specifically designed for this application. So these are becoming now very popular in the industry because as more and more AI gets used, more and more AI infrastructure gets built out, uh, distributed compute, a truly distributed compute becomes a reality. Networks become very important in the compute node. So if you know a supercomputer roughly or a GPU network, there are tons of GPUs working together. Okay, normally when you develop a software, you run it on single processor or with different threads on within a processor. But a AI training engine runs not on a single GPU. If that happens, it will take 5 years to train a Chat GPT kind of a model, but it runs for 3 months on thousands of GPUs. So all are working together. Whenever you have a distributed compute, you need to have a network which is very reliable, very low latency, and very high capacity. So there are very specific chips are getting designed nowadays for solving this problem. Okay, I'll stop here if you have any questions. Yeah, any questions? Okay, I'll move on. Okay, so so let's try to see in this and today we'll talk about the wired network ASIC. Let's try to see what all building blocks are there. This may help you to the faculty to know what kind of designs people are doing. Okay, and what kind of information they can study or they can teach their students, or when they're teaching particular courses, they can give these examples. So what is a SerDes? Okay, so SerDes is just simple serializer, deserializer. So what we're doing, we are taking parallel bits, okay, convert into serial bits, and then we're receiving serial bits, convert into a parallel bits, a simple shift register, right? But what has happened in last few years is as we start connecting more chips together, okay, we need to connect them at a very high speed. Okay, we want more speed. Now, when we wanted more speed, sending the data in parallel becomes very difficult because whenever a chip sends data to any other chip, if you send it in parallel at high speed, then what you need to know is how the other guy is going to capture it, right? So means you need to send a clock along with it. Now, if it is a 16-bit or 32-bit or 64-bit signal along with a clock, when you reach the other side, how do you capture those 60? So you have to control the entire skew of that path. So what happened few years back or around 20 years back, people stopped doing parallel communication across chips. So long time back, nowadays you would have heard about PCI Express. There used to be PCI, which used to be a parallel bus, and I'm talking about 2000s. After 2003, mostly everything is PCI Express. So what people figured out that instead of sending it parallel, I can send it serial, and I can embed a clock with the data. Okay, once I do that, when I receive that signal, serial signal, I can do a CDR, okay, clock data recovery, that I can recover the clock from the data and then sample the serial data, okay, and achieve a communication. So this has allowed in last 20 years, we used to like 20 years back to work at 3 gigabits kind of speed. But from there to now, a single channel here, we are now able to run at much higher speed. Okay. So in a decade, we went from 25 gigabits to 200 gigabits, and 400 gigabits is in standardized process. So what it means is I can send on this wire, a pair of wire, the signal at 25 gigabits per second. Around 2012-13, when we did some designs, used to be 25 gigabits. Today, we are going to deploy a chip which is going to have the same signal run. We are able to transmit at a rate of 200 gigabits per second. Okay, that many bits. So to give a perspective, we are able to send 200 bits per nanosecond. So that kind of bandwidth we are talking about. And then we are talking about 400 gigabits. Okay, in next 2 years, we will definitely achieve 400. The PCI Express bus, which we see inside our machines now, is a serial bus now. So that is one example for serial bus. Ethernet definitely is always serial. SATA and USB is also serial. Okay, but they use different protocol. But what's happening is the Ethernet and PCI Express, these two things, is driving this race for faster rate. So the more rate we add, uh, they are hungry. Okay, and that's primarily driven by GPUs and data center networks. So when we talk about SerDes, right? We said okay, it's very simple. We will take parallel bits, convert to serial, send it across. Then we need to talk about now the complex part, right? How do you do this, right? So so probably some of you would have heard about encoding, and you would have read about or teaching students about NRZ, and you would have taught about PAM4. So PAM4 is something now coming to SerDes, which are onboard SerDes. Okay. Uh, these are very complex and challenging designs, designing this SerDes. Okay. And very few vendors in market able to produce 100 gigabits per second and above design. So it's a very complex design. Whole piece of IP is extremely complex and challenging to design. Uh, So what all this IP is contained? Okay, in the transmit we have encoding and scrambling, we have pre-emphasis and FFE, we have output drive and impedance matching. On the RX, we have CTLE, that is called continuous time linear equalization. There's a DFE, decision feedback equalizer, and we have CDR, which is a clock and data recovery and more. Again, the I'm not an expert of both these designs, but the idea of throwing this terminology at you is that I would hope you will go study about this, okay, and try to understand what is happening. What are the challenge when we say that if you want to transmit a signal, a serial signal, what it means, and we'll come to the next part is more interesting. This everything here written falls in the domain of signal processing. Okay, how do you process a signal? How do you want uh, on this signal? How do you extract the ones and zeros from this analog signal? So all this is needed, uh, and that's why all this circuitry and most of this analog circuitry is added to do this. Like impedance matching. If your impedance don't match, then there could be reflection. So all these concepts are signal processing concepts. They get used. And then there is a channel. So what we're showing in these diagrams is a transmitter, there's a receiver, and there's a channel. So channel could be a board, channel could be a wire, channel could be optics. So all that, if it is wire, if it is a PCB, then how do you, when you're doing the PCB design, when you're using this chip and when you're routing it, what kind of restriction you need to do, all that you need to take into account in the system design part. So this only talks about, so this slide is only talking about the SerDes, that hey, here is this IP which can allow you to give you a very high speed connect between chips. Now let's move on to the next topic, that yes, you have the physical, you have the SerDes which is able to take n bits, convert into serial and send it to other chip, and you can get that n bits back. But is that enough? Okay. Uh, so what happens is, now from the analog part of the design, let's now move to the digital part. So what all we need to do in the digital part of this design. Okay? So whatever we saw in the previous slide, that you have this various circuitry by which you are able to recover the data and all that. At higher speed, it still has errors, which we in the industry refer to as bit error rate. Okay? So you can still find that bit error rate could be 10 raised to minus 10, 10 raised to minus 11, 10 raised to minus 12, 10 raised to minus 15. So 10 raised to minus 10 in thousands or few thousand bit, few bit, one bit is in error. So what do you do? If because when you're working at 100 gigabits or 100 bits per nanosecond, will every often you'll start finding error if the bit rate is so high, bit error rate is so high. So what people are doing nowadays is they are putting a forward error correction FEC IP into their designs, and the algorithms use a Reed Solomon, and there are other algorithms, but Reed Solomon is more famous. What it means is, you will send, if you want to send, so one of the standards is like, you are sending, there's a block of 5140 bits, but you're going to add another overhead on top of it, which is roughly 300 bits, and the actual block you transmit is 5440 bits, out of which 5140 is your payload, and rest of the 300 bits allow you to detect errors and correct them up to certain level. Okay, that's why it's called forward error correction. if anyone has studied or can go and study about optical networks or long haul optical networks. Unfortunately, this is not an interactive session, but uh, if you have heard about, there's a optical fiber link between Chennai and Singapore. Okay, that's our main one of the main internet connection for our country. There are more cables, but from Chennai to Singapore is a big optical fiber cable. In optical communication, there are very strong FECs because the signal actually gets attenuated very quickly. So there are very sophisticated fake IPs use this communication. So they are very common in optical communication, long haul optical communication. But nowadays, because of this high speed, even on the 20-inch, 40-inch or data center networks, also FECs are coming in. Uh, Now, as we said, this service is giving us a serial connection, but we need to now find with that uh, bit boundary, byte boundary. So we would be adding markers into this kind of things, and we would be all so to do these markers to do like no one is going to people are going to talk in terms of 64 bits, 32 bits, right? But when I send those bits and the other guy receives at some time, it recovers the clock and starts creating a 32-bit bus. Don't know whether that 32-bit which we send, my next 32-bit and first may get merged, and in between 32 bits it starts giving. So the boundary is very you don't know. So the first problem to solve is how do you find this problem? So there are different coding techniques are used. In the past, people used to use 8-bit NB. Then we went to 6266 when today PCI Express uses 128, 130, while the Ethernet uses 256, 256. So every 256 bits, there is one extra bit, and that is 256, 257. On top of it, there are concepts like we may pack multiple bits together, multiple lanes together, and create a fat tree. You would have heard terminology like X16 in PCI Express, or when you say 400 gigabits Ethernet, if you go and study the PCS layer of that, it actually has 850 gig or 400 gig independent lanes, but to the user it is a 400 gigabit link. Okay, so to do that, there are uh, there are different markers added into individual links, and they're removed, and that happens because every link is independent. So every link could have different skew. So when you throw bits at all these n links, and when they come back to you, you have to first make sure that you deskew them. And there are different techniques. If you study the physical layer of Ethernet or physical layer of PCI Express, you'll find out how people deskew and build that fat tree again, fat bus again. Again, these are the various standards which are defined. So as an example wise, if you take an example that there's a Ethernet MAC, the Ethernet 802.3 is a governing body for MAC standard. It controls the media access controller MAC and the physical layer, and there are various like layers here. So if you see, the left hand side is a transmit direction, the right hand side is a receive direction. So the system interface, as we go down the path towards the serial interface, so many different things happen. There's a like 250, 260 or 66, 256, 257, there's a scrambler, there's an aim insertion, there's a lane distribution, there's a fake encoder, and there's a symbol distribution, then goes out to the SerDes device, then the SerDes sits. The receive direction, we do lane alignment, lane reordering, fake decode alignment removal, X56 descrambler encoder, and then finally we get the bits. So just SerDes and this physical layer itself, there are some companies which only sell this as a IP. Okay, there are some companies sell this entire MAC layer as a IP to whoever we want to build some application using Ethernet ports. So people do that job also. Okay, just doing this itself is a very difficult job. Okay, it's not that easy to do it. Okay, any question at this point, Manisha ma'am?
No, actually, what you are telling, it's used for ASIC design. All these
Yes,
points for networking point of view,
yes.
all these points are considered. Like you said, algorithm like read Solomon. So that
Mhm.
algorithm is implemented.
Yes, yes. So if you see, these all blocks are actually digital design. Okay, they are not analog. So if you see this fake encoder decoder, okay, is the part where this algorithm is used.
Okay,
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 and
okay, okay.
this is if you go back. So if you go back in the sense that if you read this standard, okay, uh, when we used to do this same thing at 10 gigabits per rate, you will see that this block was not there. Okay, because at
Hmm,
lower
hmm,
speed, when you're transmitting the signal at a lower speed, there is not much error. The BR is very low. So you don't have to
hmm,
worry about the BR. Okay.
hmm, hmm,
But
hmm.
as we are stretching the system, we want to go to 50 gigabit, 100 gigabit. The need for adding these blocks is coming into play.
Yeah,
So this
because of the
actually
speed.
because of the speed, the physical medium, right? Because of the signal, the way the signal transmit, the attenuation and the way when we capture the signal, there is always a possibility of error. It's very difficult because of the speed to say that, oh, I'll be able to capture all the bits correctly.
Okay, okay.
And rest of the blocks, like 8-bit NB or this, these were always there because this. So anyone who is seeing this first time need to think this way that there are two different modules, and I want to communicate between them, right? Like there are two different chips, I want to communicate between them, and I want to do serially. So there are bits of data, right? And I'm going to transmit to the other side. So now, how do I know where the data starts? So how do I identify data? For all that, these coding techniques are used because these
Techniques and
techniques, yeah, these techniques allows you to synchronize with the transmitter. Okay, and then
yes,
you will have markers in the data saying that, oh, this is start of packet, oh, this is end of packet. So you would have like seen, if you have studied 60 or 66 standard, there's this 2-bit which indicate data or control, right? And in that control we have various control defined at start of packet, end of packet, idle, and some special characters. So then you look at them, and that's how you communicate between two devices. So think that you're designing a IP where the two different distinct chips I want to communicate bits across. So they were always there. What is getting added is the fake. The aim
hmm,
insertion and the alignment removal happens because to achieve higher speed, I will need multiple links. With one link, I'll not be able to achieve 400 gigabits or 100 gigabits. So I'll take
hmm.
four links of 25 gigabits, or I'll take four links of 100 gigabits to achieve 400 gigabits. And then when that happens, there could be skew, right? So I'll have to do alignments because I'll give
Yes,
all of them data. So the you can study about what techniques people use to do that.
yes, perfectly.
Okay.
Yes,
Okay. So
yes.
you're right. This is all actually is implemented. Some companies may design this on their own. Some may buy IP from someone else. So
Hmm.
there are companies which actually develop this IP. So we
Okay.
may buy it directly also. But I think your original question, are they implemented? So yes, they are implemented. Yes. Okay. So let's take an example because SerDes is very common IP. Let's take an example of a Broadcom Tomahawk 4 switch. Okay, it's a 25.6 terabits per second capacity switch. Okay, uh, this was uh, this was released in 2019, so it's like 6-7 years back. Now, what we just talked about is this port blocks where we have this 400 gig port coming in, right? Where we talk, the MAC is there, and from where the traffic is coming into this chip. Rest all blocks are designed by Broadcom in-house. Okay, they have designed a whole chip which is able to process this 25.6 terabyte. What they are doing, they are receiving these packets from these blocks, and then they're inspecting the packet to decide which other port the packet needs to go. Okay, so this entire chip they integrated 512 550 gig SerDes. Okay, and it actually acts as 64 400 gig port. So what they're doing, any port to any port, if packet comes, they're able to switch it. Okay, and on top of it, there's a lot of complicated tasks of looking inside the packet, looking inside the header, modifying the header, giving priority to some one packet over other. All these things they're doing. This is how they have structured their chip. They have multiple packet processing box. They have a shared buffer at the center where they're storing the packets, and then they're sending it out. Again, all this data which I have showing you here, it's completely publicly available. Anyone wants to search, they will also get this data. Okay, and they have a massive 80 megabyte buffer on chip. Okay, another reason I'm talking about all this today is most of our faculty or student would be aware of chips like Snapdragon or Apple or Intel chips, right, Manisha madam? Am I correct? Most of you
Yes,
know this, right? But
yes,
most, right? So that is very common because they are marketed. These chips are marketed, you know, right? But most of you don't know there's another world of this ASIC and chips where the chips are not marketed that much. Okay, okay. uh,
yes,
but they are designed. Okay, and there's another terminology which gets used in the market, which is called SOC. You would have heard about it, right, Manisha madam? SOC,
yes, yes,
right, right. So these chips we are calling it ASIC and not SOC, and there's a reason of that. So normally SOCs are the devices which are very general purpose. So it will have tons of processing chip depending on how much money you're ready to pay, and some very standard IP, like it may have a USB IP, it will have a Bluetooth, it will have some interface with speaker. So if you go and search for SoC design for mobile, you will find a very specific set of IPs present on that chip, right? And then you'll find various version of it. Someone may have 4 ARM core, someone may have 8 ARM core, someone has this USB standard, someone has a specific write format to the external storage and all that, right? And they're very general purpose. Different mobile providers will use those chip and then they'll market that. Oh, I have this Snapdragon 8 Lite, so the performance is good. They'll provide you with the different benchmarks showing that okay, on my ARM core, this runs this fast, multi-thread performance, all that. These chips are not like that. These are very purpose built. So every block here is completely designed in Verilog. Okay, it's like a digital design, very complex digital design using multiple SRAMs and thousands of flops. This design could be having millions of flops. Okay, but no one will talk about this because they are not sold out in the market. Okay, I mean at least Tomahawk 4 and 5 and 6 you will hear a lot about them because there are multiple vendors building Ethernet switches using them. But later on when we talk about Juniper chips, normally we don't talk about them because we sell them as a router. And this is a totally different world. This is not using CPU. Okay, this problem which is solved here cannot be solved using any CPU, not a ARM core, not a x86. Okay, this packet processing pipeline has to be solved using digital logic working at a very high speed, 1 gigahertz, 1.5 gigahertz. Okay, so that's the complexity we are talking about here. Okay, if there any question, otherwise I'll move to the next example.
yes,
Okay. So whatever whatever you hear about, like a lot of you would be hearing about data centers, right, Manisha madam? Like you would have hearing
yes.
about Amazon data center. There is like this cloud is the word we use, right? A lot of people
Hmm.
write application which run on cloud, right? So all these cloud deployments are basically having thousands of tens of thousands of Xeon or AMD based servers which are connected via Ethernet switches. And most of these deployments, 80% market is controlled by Tomahawk switches. Okay, Tomahawk 4, Tomahawk 5. So that's the scale at which Broadcom is working. So they're like thousands of switching devices are deployed in this data center. So it's not only the CPU which is important. These Tomahawk switches which are made this data center possible. Today in the coming quarters there'll be a Tomahawk 6 device would be getting released, and probably it's already released, and the capacity is actually 4 times of that. So in 6 years they already reached 100 terabits capacity uh, of this device. So a single device will give us 100 terabit switching capacity. The next example is close to my heart. This is what we called Juniper chips. Okay, you will see, and I could show the actual picture of a chip. This is how it looks. Okay, you will see Juniper branding. You will see a Taiwan branding because it was manufactured in TSMC. Uh, it also shows you a very interesting thing. Okay, which is that this is a package. If you see the BXX, this is a package where this chip is instantiated twice. Okay? This is a new era of chips now, new era of packages now, where you will be hearing a word called chiplet. Okay, so multiple chiplets are getting packed in a package to give you a large capacity. Okay, so if you imagine this as wings, these are the HBM memory. Okay, this is HBM memory connected to this chip at the center. This gives us a very high speed bandwidth to a DRAM. And then there's a F here, which we call as a fabric chip. Okay, I was like part of a lot of architecture team for all these three chips, and we are selling products which are based on this chip. Okay, which we externally, again, this is publicly available data. We call it Express 5 because it's a fifth generation of our chip.
The- These are switches, right?
No, sorry, I did not explain. So these are all routing chips. These are not switching chips. Okay.
Okay.
There's a very fine line between a router and a switch. Okay, and we'll come to that in next slide.
Okay.
Okay, so this package is a 28.8 terabits per second router, which has a deep buffer. Okay, so so these are the different applications where we use this chip. Okay, uh, today we are the consumer sitting here, and there is a data center sitting here. Okay, and there's a cloud. Why we show like this is because even today when we connect to Amazon data center or any data center, we don't know what's going on, right? We just have a mobile in hand, or we just have a laptop in hand, right? But we
Yeah.
connect to the data center, right? Whatever, right? So it goes through multiple layers. The way the network is built, there are multiple layers with through it is going, and a multiple point where this is drawn is where our devices sit in. Okay, and these are routers and not switches. Okay? So this was the first chiplet based design for the networking application. So we claim we were the first to do that. The package of BXX actually achieves 28.8 terabit, where the package of BXF achieves 14.4. And this allows us to build a modular system where the capacity when we say the single chip, it's a single chip 28.8 terabits. But when it's a BXF, we can use multiple chips with a BF to build a very big chassis. And we have that application. So it's like the total chassis capacity would be like 100, 200 terabits. So that level of capacity we are talking about. So I was coming to your question about the switch versus router. A router actually has to do a lot more, because a switch, what happens is its ability to look for addresses is normally restricted, could be few thousands. Okay, well, a router uses IP. So if any one of you has studied of IP protocol, IP protocol, the address is a 32-bit entity, right? Uh,
Yes.
right, and IPv6 it's become 64-bit. So you could have millions of routes possible, right? So there's a particular algorithm used uh, to look for a destination, or what we in the routing terminal call next hop. So you need to integrate that algorithm, uh, uh, the LPM problem, the fastest match or the lowest or the maximum match. So that is one part. Second part is in such a router, you may need a deeper buffer, because your end-to-end latency would be very long, and you may end up storing packet. You may storing a queue for a few milliseconds also. So that differentiates router from the switches. It also has very very high it can be very flexible. So basically, when these kinds of networks are developed by system providers, they could do traffic engineering. So there are different protocols are used for traffic engineering to give guarantee of service and all that, things like MPLS and all. So all those you would have heard word like tunnel, right? Like like on a public internet, maybe you may be working from home. Let's say at VIT, you connect from home to a VIT network. Like when I work from home, I connect to Juniper networks, right? Uh, so there's a concept called tunneling. Okay, when we all shifted to work from home, the solution was available, but it became very important that I am sitting at home, but my network is somewhere physically there, right? My office is somewhere. Now I am allowing my laptop to be part of that network. Okay. Now, if I allow that, then anyone can connect to my network, hack it, and steal my data, right? So, so to avoid that, the tunneling is used. One of the application of tunneling, the tunneling has tons of applications, but I'm just conceptually trying to tell you that the way I connect to my network. Okay, so now this involves a lot of protocol, and this involves the router to look inside the packet, trim those headers, change it based on that, some take some decision. In a basic switch like Tomahawk, those application, those use cases are not those necessary, that much necessary. But say router would need lot of such applications. So 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 because of that, our chips have very programmable and high throughput packet processing algorithms. So we have different stages called ingress parser, source lookup, destination lookup, result processor, ingress rewrite. Now all these modules here which are stored, filter, polisher, okay, these are digital designs. These are not CPU based. Okay, these are very custom digital designs, specifically designed for our understanding the needs of the solution, the speed of the solution. We cannot implement this using a x86 or any CPU. Why? Because the rate at which we are doing 28 terabits. We are processing 2 packets per 1.67 gigahertz clock, okay, or 2 gigahertz clock. CPU, you cannot do that. Processing a packet in CPU, the CPU starts falling behind. CPU cannot do event processing very fast. So these are all digital designs which are designed inside Juniper networks, very specific for us. And then we have this whole concept of what we call non-blocking network, which allows us to build, uh, uh, which allows us to connect multiple chip and give a fully non-blocking network uh, to build a big 100 terabit router. Okay, so you guys can study about what is non-blocking network and what is a VOQ architecture. Again, those words you can go and figure out. Uh, so all these protocols we develop on our own, we implement in our chip, and uh, we do stuff like retransmission and all that. All that stuff happens. And this is how the final product looks like. It's like a chassis which we build. There are line cards, there are fabric cards. There's different capacity. We are talking at 345 terabits or 518 terabits. When it's fully populated, you can achieve that huge capacity. And these are all like 10,000 watt power dissipating gorillas. Okay, if you fully populate them. So that kind of scale we are talking about. That kind of application we are talking about in Azure, in SPCOS, Cloudflare. So all these companies which you hear about, they run on this device. They're not tons of this device, the few of this device, because these are like very costly devices. They're like 500K, $1 million, or 400K, depending on what all configuration you buy. So these are designs what people do, or what in the networking industry people are doing. So it involves not only ASIC engineering, it involves a lot of system engineering, a lot of power distributing engineering, a lot of engineering, how to cool these chips and all that. So it's like even if Juniper is a networking systems company, we have a lot of mechanical designers who are allowing us to develop this chassis. And then the topic which I did not touch upon is like an entire new class of ASICs getting developed for GPU scale up and scale out networks, and that's an entire new topic, entire new generations of ASICs are getting developed. NVIDIA is already developed something called as NVLink switches, which you guys would have heard about. Uh, and industry is developing a UA-Link standard for same purpose, low latency, high bandwidth. Multi-million dollars are getting invested in multiple startups to develop this ASICs, this what we call UA-Link, or what industry now calls scale up networks. People are also working on a new standard called Ultra Ethernet, which is already out for scale out kind of thing. And NVIDIA already have solved this problem using the band. So yeah, and these are all application where people are designing this using 3 nanometer or 2 nanometer design, like cutting edge, very complex, very costly. Okay, designs are currently going on in various startups in US. Some of them are in India. They have their design centers in India. Yeah, that's about it. I covered a lot of topics. If you have any questions, I can take it up.
But fantastically, yeah, yeah. Niranjan, go ahead.
Yeah, please, please. More question you ask, it's good.
Yeah, that's the way it goes. Yeah. Yes, Niranjan. Yes. Um, okay. Niranjan, if any question, bas-
No, ma'am.
yeah, yeah.
Okay,
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 okay.
fine.
Basically, your company has developed, or rather, you have developed that switch and communication.
Yeah,
Yeah.
yeah, yeah, yeah. I mean,
Yes.
part of the team. Okay, it's like
Okay.
a big
Yeah,
team
yeah.
of people who
Uh,
do all this. Yeah.
uh, when switches or routers are there, lot of heat is generated. So what?
Yes,
Uh,
yes. So in the routing industry, so far people are still relying on air-based cooling. Uh, Lot of power in our devices is wasted to run the fans. Okay, so in the mechanical design, so definitely the chip is always having a very big heat sink on top of it, which is stuck on top of it, and
hmm,
then a particular airflow is designed to cool them.
hmm,
Uh, the industry is trying to move towards liquid cooled. The lot of GPU clusters are now liquid cooled. The service providers are not yet moved to liquid cooled because they still think liquid cooling is dangerous. The infrastructure has to change because when you say liquid cooling, you need to have pipes, you need to have pumps to pump in the liquid, run it on top of the chips and all that. But the industry will slowly move to liquid cools because it's becoming very difficult to cool these chips. But so far it is air cooled. But yeah, in few years we'll definitely will be moving towards liquid cooled solution for these
and
complex routers.
what could be the right now? You said that 400 bits will be the rate, no? Gigabits.
So the two parts. If from a Ethernet ports perspective, it is like today people are deploying 800 gigabits Ethernet network. 1.6 terabit is already coming. Okay,
Hmm,
and
hmm.
then 3.2 terabit is in planning. So when 3.2 terabit comes, that time of 400 gigabits per second service would be available. And yeah, in next 2 3 years we would see a 3.2 terabit port on a device.
Mhm.
But yeah, the industry is
Yes.
basically the GPU is and the AI is making this transition quicker. Earlier, it used not used to be that fast, but from 3 years now it has come down to 2 years. The adoption to the next generation. So
Next generation. Because of this AI compatibility, I think all these advancements are going on because AI
yes,
is now everywhere. So that integrate
right.
that AI software, the bit rate has to be other system has to be up to that level.
Yes, yes. The
Yes.
AI infrastructure is driving this revolution.
Yes.
Yes, you are right.
Yes.
Earlier also data center was driving it.
Huh.
Just that uh, data center networks is not a distributed compute problem. They needed high speed, but they were happy till 400. But from 400 to 800 to 1.6 to 3.2, some of it is driven by the AI infrastructure, which is it.
Definitely. Really fantastic, fantastic session. Manas, a vote of thanks.
Yes, ma'am. So, respected sir, on behalf of everyone, I would like to express our heartfelt gratitude to our speaker for taking the time to share his valuable insights and experiences with us today. Your journey from VIT Pune to contributing to supercomputing networks, delivering multiple generations of ASICs, and filing 10 patents is truly inspiring for all of us, especially as students aspiring to build meaningful careers in technology. Thank you for not only sharing your knowledge but also motivating us to pursue excellence with dedication and courage. We are deeply grateful for your presence and guidance. Thank you once again, sir.
Thanks.
Yes, yes, yes.
Thank you.
The really wonderful session, Harshad, because you touched right from basic to the application level, okay, a practical level, because you touched upon what kind of communication is required, whether it is by using the optical fiber or optical cable. So you touched every communication or networking part very nicely. Really thankful for the session and for taking out time from your busy schedule and sharing your valuable knowledge to the participants. So really thankful for that, Harshad, for giving such a wonderful session.
Okay.
Yeah,
Thanks, Misha. Yeah.
we definitely we will be in touch afterwards for any updates or anything uh, we required. Rather, we will be in touch with you.
No problem. Yeah. If you have any question, you can ask. I mean, you can
Yeah.
send to Manisha madam and she can forward. Yeah. Yeah.
Yes, definitely. I was telling the same afterward. If any question or if any query of any contact, anyone wants contact, I will connect with you, and you can take it ahead afterwards.
Sure. Yeah.
Yes.
Sure. No problem. Yeah.
Okay. Okay.
Yeah. Thank you.
Again, thanks a lot. Thanks a lot.
Yeah. Thank you. Have a nice
Yes.
day. Yeah. Bye.
Yes. Okay. Bye-bye.
Bye.
Bye. So participant feedback link is already shared into the chat box. Please fill the your uh, feedback link, all the details, because it will be taken as your attendance. And tomorrow we are starting our session at 3 o'clock. 3 o'clock. At the same, we are having two eminent personalities from Capgemini and from Toshiba. Again, they will be giving very good insights about the journey. Okay, so stay tuned with us and take more advantage from this session. Okay, so thanks a lot. Feedback link is shared, and fill the form, and you can leave the session. No problem.